We can go ahead and get started. I don't have a ton of material, like I said. I'm just going to go over section 4. There's not a ton of material in section 4, but the stuff you learn in section 4 is important to section 5. So keep that in mind. Like I said, it'll probably test section 5 a little harder on the exam, but section 4 is still important. So here's just what I'm going to go over. First thing we talked about was conformational isomers, different types of stereoisomers. And section 4 is stereochemistry. And then we have chirality, enantiomers, absolute configurations, that's R or S, diastereomers, and meso compounds. So the first thing we went over was conformational isomers, which if you remember that like flow chart thing, it broke it up into conformational isomers and the other one, but I don't remember what it's called. But conformational isomers are formed by free rotation of like single bonds. And then the other side, why can't I remember what that's called? But that's like cis-trans isomers with double bonds, or enantiomers, so optical isomers. So conformational isomers, they have the same connectivity but different structures. That's the definition of also a stereoisomer. So the whole premise of conformational isomers is having either an eclipsed or staggered conformation. And this is the same thing in like chair and boat cyclohexane, if you remember that one. That's the same kind of concept. So because there's free rotation on CC single bonds, molecules will rotate to get the most stable conformation. So like up here, this is the compound I have drawn out. And you can't really make a Newman projection just from the structural formula, but for visual sake. So this is just one propanol. So how Newman projections work is it's a way to look at the molecule from like head on. So like this staggered one is like here. So it's looking at it right through here. And then, wait, this is staggered. So you have a hydrogen here. This like dot in the middle represents a carbon. You have the hydrogen up top. You have the OH group here, another hydrogen here, and then this circle in the back represents another carbon. And then you have CH3 group here and 2 more hydrogens, okay? So when you're looking at it head on and it looks like this, that means that it's staggered. So all the groups in the back are in between the groups in the front on that front carbon. And that's more stable because as opposed to eclipsed, which is where everything is lined up, all of these electron fields are going to be touching each other, are going to be too close. So staggered conformation gives you the most amount of distance in between electron domains. And this is eclipsed right here. And you show eclipsed by, it really looks like this, but you can't draw it like that. So you normally turn it like barely. So you can see the groups in the back. This is eclipsed. And then we also did conformational analysis, which is the thing where you had like the graph and you had different rotation angles and then the energy of those molecules. So the most important thing you'll need to know is just that staggered is more stable than eclipsed. And you can go from eclipsed to staggered by rotating 60 degrees. Okay, so to the other side of isomers, we have chirality, which is the premise for the rest of the optical isomers. So to be chiral means that a molecule's mirror image is non-superimposable. So its mirror image is a different molecule. And to be chiral, you have to have a chiral center, which needs to be an sp3 hybridized carbon. So all single bonds that has 4 different groups attached to it. And that is called a chiral center, sometimes a chiral carbon. And achiral means that a molecule's mirror image is superimposable. So its mirror image is the same molecule. And an achiral carbon has 2 or more identical groups attached to it. So let's see. So I have a few examples here on that. So this molecule here, okay, I want to know if it has a chiral center. So you just go through the carbons and determine if it has 4 different groups attached to it. So I know these 2 can't be chiral centers because they have 3 hydrogens. This one in the middle might look promising, but I have a chloro group here, have a hydrogen here, and then I have 2 methyl groups on either side, which are identical. Okay, so there's no chiral center in that molecule. This one down here, this is 2-butanol. Okay, so again, these carbons I know cannot be chiral centers because they have more than 1 hydrogen. I need 4 different groups. This carbon and the second carbon, I have a methyl group on this side, an OH group here, a hydrogen, and also an ethyl group. Okay, and those are 4 different groups. So this carbon here is chiral. So I have a chiral center on C2. These down here, the rings can get a tiny bit confusing. So we'll go through a few of those. So I know all of these carbons on the ring cannot be chiral because they have 2 hydrogens each. This carbon right here, so I have a methyl group here, and then I also have a hydrogen in the back that's not pictured. And I also have these 2 sides of the rings on either side. So this side of the ring and this side of the ring are identical. Okay, so those are actually the same groups. So this would not be chiral. Mm-hmm.
So when you're looking at chirality, the entire group on each side of the carbon is considered just 1.
Mm-hmm.
So
Yeah. Yeah, if you have like a chiral center and you're looking at like this group over here, if it's like, I don't know, something complicated, something like that, then you would look at this entire group and that'd be, it's not just what's directly next to it, it's everything on the other side. Okay. Okay, so in this case here, again, I know this, and this carbon cannot be chiral because it has 2 hydrogens each. These 2 cannot be chiral because they're not sp3 hybridized because of that double bond. They're sp2 hybridized. So this carbon here, again, I have the methyl group here. I have a hydrogen in the back. And then I have this half of the ring and this half of the ring. So this half of this ring has a double bond, okay, and this side does not. So the 2 halves of the ring are not identical. So those are 4 different groups. So this would be a chiral center right there. Does that make sense? Okay. So in enantiomers, if a molecule is chiral, again, that means that its mirror image is non-superimposable. So a pair of mirror image molecules that are not superimposable are enantiomers. And we have enantiomers when they have 1 chiral center, then you have 1 in S configuration and 1 in R. And what's different about each enantiomer is that it rotates polarized light in different directions, which if you don't remember that whole spiel. So polarized light just means that it's passed through a filter, which only allows light waves that its oscillation is in the same direction to pass through. So you'd pass it through the filter to polarize the light, and then pass it through the sample, and then it'll either, if they're enantiomers, they will either rotate the polarized light to one direction or the other, so to like the left or the right. And you can only figure that out by just experiment. So if it's like an S configuration, that doesn't necessarily mean it rotates light to the left. And each enantiomer will rotate light in the same angle, but in opposite directions. So I have an example here of a pair of enantiomers. So we have a chiral center here because this carbon has 4 different groups. Let me get my pen. Let's do. So I have this carbon here, and it's connected to a methyl group, an OH group, a hydrogen, and a chloro group. Okay, so there's 4 different groups. So I know this is chiral, so I already know that its mirror image is going to be different. But if I reflect this over, why is there a bug on me, please? If I reflect this over a mirror plane here, it gives you this, which is a different molecule. Would you guys like me to build that, or do you think you got that? Okay. So if you were to build it, then 2 groups would not match up if you tried to flip it back over and superimpose it. But you know that the mirror image is not superimposable because this is a chiral center. Okay. So, so to figure out which enantiomer is which, you have to know its absolute configuration, which you figure out by assigning priorities to all the groups around a chiral carbon. And priorities are determined by the atomic number of the first atom connected to the chiral carbon. So the same thing as like when you did E and Z configuration and assigned priorities. There it's the same concept. So you assign priorities to all your groups based on their atomic number. If the first atom is the same, then you just move on to the second set. The least priority group has to be in the back to determine absolute configuration. So if the least priority group is not in the back, you have to switch it in the back before you can determine anything. So if 4 is in the back, we ignore 4, and we're only paying attention to 1 through 3. So if 1, 2, 3 priority groups are arranged going in clockwise direction, then it's an R configuration. If counterclockwise, then it's an S. And if you switch 2 groups to put the least priority group in the back, then your configuration flips. So always try to remember that because you'll get messed up if you keep it the same. So I have a few examples here. I'd like this out of the way, please. I can't even see it. Okay. I think that's what it was. Yeah, okay. So your first step in assigning R or S is finding your chiral center. So this, if you want, you can switch to structural formula. I typically do that because I just like structural formulas better. Okay. So just keep all your lines, wedges, dotted lines in the same places if you're going to switch it. So, it's killing me. Okay, So from this line structure, okay, we can tell that we have a methyl group coplanar to this carbon here. We have an ethyl group on the other side, also coplanar. And we also have an OH group and a hydrogen. Okay, so we know that those are 4 different groups. So this is your chiral center. So now we can assign priorities. We have an OH group, so we know that'll be our first priority. Oxygen has the highest atomic number. Hydrogen will be 4. And then between methyl and ethyl, ethyl has 1 more carbon. So when you get down to canceling out, you'll be comparing a hydrogen and a carbon, which carbon would have a greater priority. So your ethyl group will be 2, methyl group will be 3. Okay, so your least priority group is already in the back, so we can go ahead and rotate. So from 1 to 2 to 3, we're going, is that clockwise? Yeah, clockwise, which is our configuration. Okay. So next one, I wish I wouldn't have drawn these so small. Okay. So in this one, again, these two here cannot be chiral carbons because they're not sp3 hybridized, and these cannot be because they have 2 hydrogens each. But this one here, we have an OH group in the back, so we can assume we have a hydrogen in the front here. Okay, and then we have this side of the ring, which has a double bond, and this other side of the ring. So the sides of the ring are not identical. So this is our chiral carbon. So we can go ahead and assign priorities. Okay. So OH will again be 1, and hydrogen will be 4. So on this side of the ring, we have a double bond, and your double bond, again, you can think of it like it's connected. This carbon is connected to this carbon twice. So this side of the ring will have the higher priority because of that double bond. 2, and then this side will be 3. Okay, so now we need our least priority group in the back, which it is not right now. So I'll have to switch 1 and 4, because 1 is in the back right now, to put 4 in the back. Okay, so same priorities, 1, 4, 2, 3. But now that my least priority group is in the back, now I can rotate. So from 1, 2, 3, that is counterclockwise. So that would be S configuration. But from the original molecule to this molecule, you switch 2 groups to put H in the back, so you can determine the configuration. But when you switch 2 groups, you flipped the configuration to the opposite configuration. So if this is S, that means that the original molecule is in R. Okay, one more of these. That is a bit bigger. Okay, so this is my chiral carbon, right? Because it has this methyl group here, carboxyl group on this side, OH group, and also a chlorine. Okay, so assigning priorities, I have 2 carbons, a chlorine, and an oxygen attached to that. So which one's going to be my first priority, my friends? Chlorine, right. So it is 17 in the atomic number. Okay, so chlorine will be number 1. Out of oxygen and carbon, oxygen has a higher priority after that. So this OH group will be 2. And then when you're comparing methyl group and this carboxyl group, this carbon is connected to 3 hydrogens. This one is connected to 3 oxygens. Because it's double bond, you can again think of it like this carbon is connected to this oxygen twice. Okay, so this carboxyl group will have higher priority over the methyl group. So now that I have my priorities set. I need my least priority group in the back, and it is coplanar right now. So I need to switch 1 and 4 again. Okay, and it won't always be 1 and 4, by the way. It's just been a coincidence. Okay. OH stays here. Or not 1 and 4, 2 and 4, my bad. Sorry. This will be methyl group. And chlorine will stay in the front. So OH is in the back right now because the dotted line means it's in the back, and I need the methyl group in the back. So I'm going to switch, and OH is group 2, priority 2. So I'm going to switch 2 and 4 to put 4 in the back. Does that make sense?
Yeah.
Yeah. I didn't mean to mess you up. Sorry. Okay. I'm going to have OH down here. So I just switched this methyl group and this OH group. So OH is down here now, and methyl is in the back. So same priorities. 1, 2, 3, 4. Okay, so now the 4 is in the back. Now I can rotate. So 1, 2, 3. It's going counterclockwise. It's S configuration. But again, from the original molecule to here, I switched 2 groups. So I flipped the configuration to the opposite configuration. So I have to flip it back. So if this is S configuration, that means the original molecule was an R. Okay. And we ignore 4. Hold on. Because the carbon to least priority group bond is your axis of rotation in these types of chlorobonds. Okay, so let's pretend these is 1, 2, 3. If 4 is in the back, then you're only paying attention to this. Okay, so that's why we ignore 4, is because this is the carbon to 4 bond is your axis of rotation. Does that make sense? Like a steering wheel. If you remember him doing that in class. So that's why you ignore 4 if it's in the back.
So when we do the flip of like 2 groups, like moving 2 groups, whatever we get for like that molecule's configuration, that won't change even though we flipped it to the different one. Like it's really just telling us like the original is the reverse. If that makes sense. Like,
What do you mean?
Like,
So when we changed 2 groups, we did change the configuration.
yeah.
Because to make an enantiomer, if you remember that, to make a mirror image, you flip 2 groups. Okay, so when you flip 2 groups from the original molecule, you actually make that molecule's enantiomer, which is the opposite configuration.
Okay.
Any more questions on that? Okay. So the next things we talk about is when molecules have more than one chiral center. So first case, we have diastereomers or diastereomers. So diastereomers are when 2 molecules have the same connectivity but different structures, so they're still stereoisomers, but they're not mirror images. So, and they have 2 or more chiral centers. So when you have 2 chiral centers, you can either both be an S, you can both be an R, or you can have 1 S and 1 R. So in this first case up at the top, on the left, I have 2 carbons here in S configuration. And then when I flip it over a mirror plane, they'll switch to both R configurations, okay? So these are 2 stereoisomers that are mirror images, and they are not superimposable. So these are enantiomers, okay? But in the second case, if I have like an SR, or if it was RS, and then you're comparing it to SS or SR or RR. So these are still stereoisomers. They still have the same connectivity, but different structures, but they're not mirror images. Okay, so these are diastereomers. Make sense? Okay. And then the last case is meso compounds. So meso compounds have an even number of chiral centers, and they have to be in the opposite configuration. Okay, so meso compounds have, this should be a triangle here, but they have to have a line of symmetry somewhere in the molecule, which causes those two chiral centers in opposite configuration to cancel each other out. So meso compounds with that line of symmetry, they do not rotate polarized light at all, because those two chiral centers will cancel each other out. And if you reflected this over a mirror plane, meso compounds, mirror images are superimposable, so they are the same compound. So just remember, you have to have an even number of chiral centers in opposite configuration, and you have to have a line of symmetry somewhere in the molecule, which causes those to cancel out. So even if you have a molecule where you have two chiral centers in opposite configuration, but you can't draw a line of symmetry, then it's not a meso compound. Any questions? Okay, well, that's all I got. If you guys don't have any more questions.
Are you gonna do another study session before the final?
Yeah, I'll do one on section 5.
Like on final?
Yeah,
Like, we'll probably like after break.
yeah, probably the week before finals. And section 5 does touch on some of the section 4 stuff, so it'll be somewhat of a small review on section 4 as well. But yeah, I'll probably do that the week before finals. Okay, my friends. Abigail, you have any questions online?